This is the second part of the series, how to put together a simulation of a dynamic system in Rhino, Grasshopper, and Python. In this part, we will introduce boid behavior into the system, where each boid steer based on its neighboring boids. The local interaction between boids appear to be able to produce similar patterns of bird flocks as a system behavior observable in real life. We will create an implementation of the three boid behavior, alignment, cohesion, and separation in our simulation based on the description from the references. We will be using the previous setup that we have made in the previous part, which is to move 5 boids over time. So as previously mentioned, we're going to insert our processes, which describe the boid's behavior, alignment, cohesion, and separation in between the setup and move. And so let's go ahead and disconnect this and try to insert something here. Now let's begin with a Python script. We're going to plug this in to X, and in order to locate neighboring boids, what we wouldn't be able to do here is to maintain this as item access. With item access, what we get here, if we print X, for example, we are not getting the full set of boids instances. So what we couldn't do is to, let's say, refer instances 6AF with the 6B0. So what we need to do is to convert that into list access. So we get a list of the boid instances as one single operation. So what we can do now here is to build 2 for loops, boid 1 in X, for boid 2 in X, from the same list, but we also want to avoid looking for the same one. So if boid 1 equals to boid 2, then we're not going to process it. And the next thing that we want to do is to be able to define a specific radius for the search. So let's measure it in Rhino and see approximately what kind of radius we are looking for, and go ahead and create a new number slider, and let's rename this as R for radius, the search radius, and hook this up. Now what we can do here is to, before we do anything, we might want to visualize this 25 radius here. So what we can do is to extract the boid 1 position as A. So let's go ahead and make A as a list, and we append the boid 1 position into A. What we should get here is something here. Yeah, there's an indentation here, which we haven't got anything yet, so we'll just put a pass here, then it should run. So we should get 5 points here. Need to reset this. The move node has run previously, so I've reset the instances, and we can visualize the radius or the search distance using a circle node from Grasshopper. Plug the radius into and the point as the center point of the server. Now let's look at how we can filter out some of the neighbors. So for example, this boid has no connection to this based on the radius of 19, for example, but it has a connection, or it should look for the specific boid here because it's within the range as specified here. So let's try and do this. So the first thing we need to do is to find the distance between boid 1 and boid 2. So one way to do it is to take the position of the boid minus the position of the other boid, which creates a vector, and which we can measure the length of this vector. So let's do this here, position minus boid 2 position. And we find the length here. So let's go ahead and print this to see whether or not we are getting numbers or any errors. So we're getting numbers here. Now let's go and make it a variable, and to say, to put a conditional statement here to say if the distance is lower than or equal to the search radius, then we'll do something with it. So let's go ahead and print distance boid 1 or 2. Right. Okay, so there are only 2 of them that is within range. Let's change the okay, so there are 2 pairs that is within range, which is likely to be this ones here. These ones are not in range, so this is basically from one of this to the other boid, and from this boid to the other boid. Now from this point, we have we found the nearest neighbors. We need to build the specific boid behavior. So let's start with alignment. So alignment, if we refer back to the diagrams, is the average vector of neighboring boids within the range. So let's have a look at how we can obtain this. So we have reference to boid 1 and boid 2 here, and we can find the boid 2 direction. So if we print this, boid 2 direction is here, and we want to add them all up and divide it by the number of boids that is present within the neighborhood. So what we can do here is to create a new variable within boid 1 to store the information. So let's say boid 1 alignment equals, and we want to create a vector here. And in order to create a vector in this context, we need to import Rhino geometry, and we use RG vector 3D and create a new 0, 0 vector. And what we can do here is to add the direction to the alignment vector, which is 0, 0, 0 initially, but when we add additional vectors to it, it will modify it. And the next thing we want to do is also to keep track of the number of vectors or boids within the neighborhood. So let's go ahead and create another variable called alignment counts, and we want to add 1 to this alignment counts within when we found a boid that satisfy distance is lower than the defined radius. Now once we have this information, we should be able to print boid alignment here. And one way, when you print multiple things, one way to look at the specific print statement is to add a label to it. So we should be able to get some of this here. So some of this doesn't have any, which is expected because it couldn't find any neighboring boids. And from this point, what we can do at this level here, so we have already completed searching for neighboring boids at this point, at this level here. What we need to do, because we want to find the average vector of neighboring boids within range, we also need to, while we have already added up all the average vectors, all the vectors, but we are yet to average it. So we're going to average it using the alignment counts. But before we do this, we also need to take into account that alignment count could be 0, and we can't divide a vector by 0. So we create a statement here, conditional statement that says if alignment count is greater than 0, this is a shorthand, then we'll divide the alignment vector with the alignment count. And now here we have the boid alignments, and if we want to examine it, we can add a new output here. And boid alignment. Yes, I haven't set up a list for B yet. So this should give us the output for the vectors. And let's take a look using a vector display to see what the alignment is. So as expected, this is the alignment vector in green, as highlighted. This found the another boid within range and found its alignment. So this is the same as this. And if we increase our search radius, what that does is, for example, if we take this, for example, the alignment vector is the average vector of other boids, the vector of other boids within the range. We are going to rename this to alignment, and we are going to implement the other two boid behavior, which are cohesion and separation. We'll start with cohesion first, which is very similar to alignment. So what we can do is to copy the node, and let's rename it first, cohesion, and we will keep it as the same in terms of radius for now. We can modify it later with a new slider connecting to R for the cohesion node. And so activated the editor for the cohesion node, and because we have only just copied the alignment node that we made previously, we need to make some adjustments here. So the first thing I'm going to do is to rename some of the variables. And we are going to edit specific points because cohesion is slightly different from alignment, especially around this area here, because it's about, if we refer back to the diagrams again, um, cohesion takes the vector from the boid position to the average position of the neighboring boids within range. So what that means is that we, instead of taking the direction of the neighboring boids, we need to find the average position of the neighboring boids. So instead of direction, we need position here. So at the moment, this is a center of mass. Um, just to make it clearer, we can make it local center equals the cohesion. So this is the average point of the from the neighboring boids, and the local center could be used to create the vector. Now let's try and visualize this. So we've turned off the preview for the alignment node. Let's try and do a back to display here. So what we have here is that we have the vector to the center of the neighbors. So in this case, like for example here, the center of the neighbors has only one neighbor, so it's pointing towards this neighbor as an example. And with this node here, this boid here, which is different because it has two neighbors, and the center of the center of the average center of the neighboring boids is at this point here, and it's the same with this one. If we take this boid and find its neighboring boids, and the center of the two boids here is at this point here. It might be easier if I take increase the radius, perhaps, that allows us to look at, let's say, if we consider everything together. So what we can do here, what we can see here is, for this boid, it has 4 neighboring boids here, and the 4 neighboring boids, the center of mass for this, the local center for this 4 boids is at this point here, and we're creating a vector here. That's what this does. The local center minus boid 1 position. Boid 1 position is here, for example, in case of this, in this specific example, the local center is where it founds all the local neighbor within the range. The local center is this point here, which is the addition of all the position of boids within the neighbor, and we divide it by the number of neighbors within the range. Now let's go ahead and create the first boid behavior. Again, we're going to make a copy of the alignment behavior that we have made initially because the separation is very similar to alignment or cohesion with some differences. Um, we'll rename it separation, edit, go ahead and make a new variable within boid 1. Again, we name the counter here, and rename this as well. And the specific area that is different is this line here. And if we refer to the diagrams, we know that separation is about average vector from neighboring boid's position to boid position within range. So we need to edit this line here. So instead of boid to direction, which is the neighboring boid's direction. So for example, this is boid 1 and this is boid 2, and its direction is this vector here. Like in the alignment, what we need to do is to find the neighboring boids, which is boid 2, and we need to find a vector between boid 2 and boid 1. So what we can do is to get boid 1 position. Let's say this is boid 1 and this is its neighbor, minus boid 2 position. Right. So now let's see if this comes out correctly. Let's turn the vector display on. So now it's quite easy to mix up the position of this. So for example, if we have boid 2 minus boid 1 position, then it becomes almost like a cohesion behavior. But boid 1 minus boid 2 appears to be correct here. So let's say we have 5 boids here. These 3 boids doesn't have any neighbors within the range, which is 19 here. But this has a neighbor, which is this boid here, and this boid here has a neighbor, which is the one around the cursor at the moment here. And we know that this vector here is basically this point to this point. Now that we have computed all the vectors for the boid behavior, we can let me visualize it here. So we know that with this setting for a 19 search radius, only 2 of them has neighbors, which is towards each other. Now each of the behavior results in a separate vector here, and what we want to do here is to be able to combine this to guide to steer the boid in the next move. So let's go ahead and create a new Python node. In this instance, because what we did in the, if you remember in previously when we created alignments, cohesion, and separation, we have we store the specific vector within the boid itself. So what we can do is, instead of creating an output from each of these, um, we can link it to directly to the instance. And however, what we need to do here is to create a way for this to run before this node here, because for Grasshopper to recognize that um, the dependencies, if you remember from previous from the previous part, um, whenever I press this button, for example, um, everything that depends on this button would update, and we need to force that we need to force all of this to happen before we combine them. So what we would do here is to set run, and we will switch it to list access, so that it doesn't actually do anything, as long as in case we have something like, for example, B is plugged into here, then if we leave it as item access, it will run 5 times, and if we have many many boids in this system, then it would get stuck. So what we want to do here is to add a new output for each of the behavior here that we have implemented, but we're not going to add anything to this output here. It's purely just to make sure to force this node to run. Just to check that's there nothing going through. There might be something going through here, which I'm going to remove. Okay. So this is orange because we don't have anything in here. But what we can do here is to go ahead and say X alignment, for example. We can now reference the specific variable that we have defined earlier. So alignment, cohesion, and separation. So we can run this for each of the instance of boids with that we set up earlier. And we have forced it to execute or compute the boid behavior. And now what we need to do here is to unitize all the vectors. So we are keeping only the direction when we use it to steer the boid. And we will unitize the direction as well. Of the boid, and what we can do is, in order to make use of the alignment, cohesion, and separation, we can add it to the direction to change the direction of the boid. And after doing this, what we can do is to unitize it again and to set a specific length of this vector. So if I remember correctly, we have it set at 5 units. So we will do this here. can connect it to move. Or if we want to draw it, we can do that as well. And just to visualize what I meant by unitize here, because we did it in this instance. There's a unitize node, unit vector node here that we can use to modify. It's basically converting, instead of having length on the vector itself, we're changing it so that is at 1 unit. So we're retaining the direction only. So what we have here, for example, if we visualize it, what we have here. So all I'm doing is to copy the drawer node that we made earlier, which extracts the point and the vector, the direction of the instance of a boid. And what we can do is, again, unitize this and display this. So this is the current vector, or this has run already. Let's disable this and reset. So this is the current vector. The reason why it was pointing at a different direction is because we have already combined everything, and I want to show you what it looks like within the code itself. So what the code does within what is written here, basically what we're having here is the unitize. So we unitize the alignment vector, unitize the cohesion vector, unitize the separation vector, again unitize the direction vector, and we go ahead and add all of this. So let's try and visualize that as well. Let's add a few of this. And again, let's create a new So what we have here is the new direction. That is as a result of the combination of the alignment, cohesion, and separation vector, and its original direction. And as you can see here, we're up to this point. And all this does, unitize and multiply it by 5, is to control the magnitude of the direction vector. So let's go ahead and do this. So as to visualize it. Unit vector, 5. So this is the resulting vector that we're getting in terms of if we now activate the move node, it should this point should now move in this direction. It is now time to reconnect what we have done so far with the node we created previously in part 1 to run the move function for each Python boid instances. At this point, let's refresh our memory, looking at the whole structure. We have defined a Python class called boid in this node. We have created instances of the boid class in the node we named setup. And we have introduced a set of functions describing the rules for the behavior for each of the boid instances. And we have combined the computed vector of alignment, cohesion, and separation to modify the direction of each boid. And now we will use the node we named move to modify the position of each boid using the new direction. Notice that we have included new processes to run per iteration. So we need to relocate the button and the trigger here, because otherwise if we connect this directly, only the move function and the draw function will run when we trigger the node. So now let's remove this and let's disable the visualizations that we have built to visualize what we have done within the node itself. And we will re-enable it, and I'm going to give it a name where we combined all the vectors, alignment, cohesion, and separation, as well as the direction of the instances. I'm going to go ahead and reconnect this, and let's zoom out a little bit, because now that we have included additional processes and we wish to iterate anything that comes downstream from these three nodes here, we need to relocate the button and the trigger. So let's delete these ones here. Now we can add a run inputs here, very similar to what we did earlier with the move node. And let's rename it run. Now let's group them together with one Boolean parameter. And similar to what we did before, we can create a button here and a trigger. And we can specify a specific time interval for it to trigger. So let's try running it with the button. So every time I press and release the button, everything downstream from this button is executed, but not the ones that is not connected to the Boolean parameter here. And we can press this button to reset and repeat the process again here. And we can also use the time interval to run the downstream nodes. Now that we have it working for 5 boids, let's try it with more. And to do this, I'm going to reference more line geometry from Rhino, which I made previously. So remember, we are referencing some line geometries to control the initial condition when we create the instances. Now I've created a set of lines here previously, and I'm going to reference them into Rhino as a different separate nodes, so we can go back to the 5 line geometry if we wish to test certain things that we want to look at. So now that it's now referenced, again click the refresh button, reset button here, and let's try running it. Now that we have this working, how do we get to the bird blocking like patterns? There are 2 points to control here. The search radius from the neighboring boids, which we can specify different radius for different behavior for alignments, cohesion, and separation separately with the inputs here. And the second thing that we can control is the weighting of the influences for each vector generated from alignments, cohesion, and separation. Now let's go ahead and add the weightings here. So we name our variable weighting for alignments, the weighting for cohesion, and the weighting for separation. So in order to use the weight to modify a variable, what we can do here is to multiply it with the name of the variable. So x dot alignments is the vector that we compute from the previous process. And we'll multiply it by a variable here, which we'll plug slider. And the same for weighting for C and the weights for separation. Right. So now it should become red because we haven't specified any numbers here. Now let's insert 3 sliders from 0 to 0.0 to 0 to 1.0, and let's plug this in. And now let's try and make alignment 1 and resets, and let's try running it step by step. What we should see is that they're trying to align to each other, very similar to what we had before. Now let's try and set this to 0 and set the cohesion to 1. And let's try and run it. What we can see is that where we have a specific radius, they tend to cohese towards the specific local neighborhood. And that's controlled by the radius here. Let's go ahead and reset this, and let's try to set this separation to maximum and see what happens. And as expected, all the boids disperse. Now let's try different radius for alignment, cohesion, and separation. And let's try to set a specific ratio here, and you can try it out yourself if you run this, and you can see if you have different settings here, you can get different behavior.